taking all the variables we've learned about and applying them on the global scale. Uh, think of it as if you were to look at the Earth over the last 20, 30 years or whatever, where would high pressures typically be located at different times of the year? Where would low pressures be located? There's an actual global circulation that doesn't just have all these little things going through it. So I wanted to start at 250 millimeters, the jet stream. This is the last 7 days. So notice in the desert Southwest down here, we've had a big ridge for days on end. For the last 7 days, it has not moved. And at the same time, we've had a general trough, low pressure, just to the west of Hudson Bay that kind of oscillates down a little bit, then moves up. So, and in between where we live, we have the jet stream this time of year. It's actually a little for this time of year. So it's interesting that we have a very high pressure area down here. We also have high pressure out over the Atlantic this time of year. So this is a normal pattern, actually. A little bit stronger on the low to the north, a little bit stronger on the high to the south, making a stronger jet stream. But overall, this would be a typical summertime pattern. Now, as little pieces of energy in the central U.S. get a little stronger, then move east and come on out. So one of the things we're going to talk about this week is the difference between a short wave and a Rossby wave. A Rossby wave is a very long wave pattern. If you looked at the top of the U.S. or from the North Pole down or whatever, you would see areas of low pressure. And they tend not to move a whole lot. Over the course of weeks, this might shift from here, maybe out to the west coast, or maybe further east. But anywhere it is, other short waves, the little features, are going to tend to intensify when they come into that circulation, the broad low that's here. So they get a little stronger. That's why they've been hitting Ohio, West Virginia, even New England and all with more precipitation and a stronger amount of energy because of a Rossby wave versus a short wave. So with that, let's take a look at just the surface pattern with this. Notice there's several low pressure systems out here over the mid-desert Southwest. Why are they there? Well, it gets really hot out there, especially this time of year. So what happens is the air tends to rise, very dry air typically. And remember, hotter the air, the lighter the air is. Well, you actually create a surface low pressure right here called a thermal low. And we saw above it was a big high. So it just flips it. High pressure, remember, in the thermal environment, when it's very warm, pressure is slower to change into vertical. So you wind up with a high pressure above it. Perfect example. Now, there's a high pressure off the Atlantic coast as well, typical for this time of year. And for other times of year, typically around 30 degrees north, you're going to find high pressure. Low pressure is going to be more closer to 60 degrees north. And it's a little bit further south than that, but there's a lot of low pressure right along here. Typical of our atmosphere. It moves a little bit further north in the summertime and a little bit further south in the wintertime. That's why you hear about the Bermuda High more in the summertime than you do the wintertime. So finally, let's just look a little bit at Climate Prediction Center. This is El Nino, which is part of a global circulation, or ENSO. ENSO can mean either La Nina or El Nino. El Nino means temperatures are warmer than normal in the Pacific. Guess what? This is temperature anomaly. And you can see right across the equator there, temperatures are slowly getting warmer and warmer than normal. This means we're going into maybe a very strong El Nino pattern. And these have global implications for the weather. Before this, we have been in a La Nina where the temperatures were actually below normal by 1 to 2 degrees. Now you can also see another called north circulation. We'll look at it a little bit too, and you'll see that it is below normal right now, a little bit, not real much, and it was above normal earlier. And that has an impact on the eastern U.S. and much of the eastern half of the United States weather. So it's something that in the wintertime especially, meteorologists try to forecast this out into the future because it may impact the next 7 to 14 days of weather. And these patterns can tend to stay there for a while. They're not going anywhere very fast. You notice we had started out fairly negative the beginning of May, bumped above early May, and we stayed there well into June. So these are long-term patterns that impact what's happening in the United States. So now that we've talked about that, so what are some of the primary circulations that go with this? So if we had a non-rotating Earth, we don't. We would basically have the sun getting very warm over the equator. The coldest would be over the equator on the other side of the globe. And we would get these big circulation cells. But we don't. And what we wind up with is from 0 to 30 degrees is one set of winds moving from the east, typically, towards the west. North of that, we have the westerlies where we live, 30 to 60 degrees north. And north of that, we can have some polar easterlies. So this is the general rotation with that. And with that, we have low pressure around 60 degrees north. We come a little bit south and north, a little bit further south in the winter, a little bit further north in the summer. High pressure around 30 degrees north. Low pressure is definitely along the equator. Intertropical convergence zone. We saw easterly winds, and they're moving towards the equator there. That area is where the winds tend to rise up. And here you see a pattern typical of winter and summer. And notice how the high pressure shift further south in the winter, the 30 degrees north, becomes a little further closer to the equator. In the summertime, it moves back to the north. So with that, there are two subpolar lows, the Aleutian low, Icelandic low, and the polar front sets up along, dividing where the colder air is. Over the pole, there's something called a polar vortex. You're going to hear about, you can read articles about this all the time anymore, because it kind of influences how much cold air gets into the United States, the mid-latitude area where we live. The stronger it is, the less air can get out of it. Kind of traps it into circulation. The weaker it is, the more air can get out of it. So we just looked at a pattern where I showed you the waves going through. And this is what it typically looks like, ridge high. The tropopause, meanwhile, down over the equator, it's fairly uniform, fairly high up. Over the poles, fairly uniform, fairly low. In between, where we live, it fluctuates. So there'll be some days when a strong, low, cold air mass is coming in, it drops well down. Other times when a warm air mass is coming in, a warm front's moving up, it will move up. So you can see we're kind of in the latitude where the tropopause varies a lot. Actually, many meteorologists can use the tropopause to help forecast how intense circulations might be. When we see the tropopause getting lower and lower, we know we have a very strong upper level energy system coming in, which may impact and help produce very strong weather for us. The trade winds develop an inversion because they're moving across relatively warm ocean water, moist down there, and above it they're fairly dry. Intertropical convergence zone moves with the sun. Why doesn't it move as much over the water? Notice the Pacific and the Atlantic. It doesn't move a whole lot. Over land, it moves a lot. The reason it doesn't do that is because the water has a very high specific heat, takes a lot of energy to change its temperature, and it doesn't change a whole lot in reality compared to land. So over land, the tropical convergence zone moves much further north or further south. And because of that, it sets up what we call monsoonal circulations. So if the intertropical convergence zone moves north of India, the winds are coming from the south into that. Well, that means they're coming off the Indian Ocean, the Arabian Sea, where lots of moisture is, so they get very wet. In the wintertime, on the other hand, the intertropical convergence zones move down in south of India. Where are the winds coming from? They're coming out of Siberia. Not a whole lot of moisture in Siberia. So we can talk about these highs. On either side of the high pressure, depending on the flow, and think about it, the flow around the high is clockwise. So if the high is centered over the middle of the Atlantic, if you live on the east coast of the United States and you're influenced by that high, you're having winds coming out of the east-southeast. What's to the east and southeast of the United States? A lot of warm, moist Atlantic water. Oh yeah, San Diego. What happens there? The winds are coming out of the north. You wind up instead with very dry, relatively cooler air. Not real cold, but cooler air. So they wind up with not much moisture, not much rainfall from this kind of a pattern. Whereas the eastern United States gets lots. And here you can see these atmospheric currents influence the ocean currents. So here's the North Atlantic gyre right over here, and it's right over top of it is the mid-latitude, mid-tropical cyclone, anticyclone, excuse me. So you can see it just sits there and rotates, and it causes the water to rotate. That's why we have a Gulf Stream coming up the east side of the United States and heading towards England, which actually helps keep Iceland and England a little bit warmer than they would otherwise be. We have a monsoon circulation in the United States. That low pressure system that you saw at the surface out there to the west, it was developing high pressure aloft. Guess what? That pulls moisture in off the Gulf of Mexico, southwestern Pacific, southeastern Pacific, and into the United States there. That's why Arizona, New Mexico, western Texas, and all get a lot more rain this time of year. We talked about Rossby waves. They can be blocked. Notice that we showed you that high pressure system that was basically cut off out there, not moving. That's the kind of blocking pattern we have. And when that happens, it can set up weather systems that persist for days. This was a blocking pattern that occurred back in the summer of '93. Record rainfall in the Midwest. You can see here way above normal. So jet streams, basically, they're going to be the closest you can get to the tropopause. They're going to tend to form in the upper part of the troposphere because that's where the air contrast is greatest, temperature contrast. And that's what they're looking for. That's why they develop. The more the temperature contrast, the stronger the jet stream. Remember, we've already talked about how winds blow along isotherms, and the jet streaks are just a little bit stronger winds. And they shift north and south. The polar jet stream will move well south in the wintertime, maybe even along all the way down to the Gulf Coast. Further north in the summer, this time, it's kind of in the middle of these two, which is kind of an unusual pattern for summer, I got to admit. And there are short waves that move through these Rossby waves, like I showed you, digging deeper. When they do that, they create divergence aloft. This is what triggers the low pressure systems at the surface. Believe it or not, the low pressure system typically does not start at the surface. It develops aloft first. You have the trough of low pressure, you have divergence, and you begin to pull the air up, which develops low pressure at the surface. We're going to get a lot more into that. Here is where they basically occur. You looked at a jet streak, where the strongest winds are. Left front, right rear are where the divergence in the air tends to lift. We talked about El Nino and La Nina and how we're moving into an El Nino pattern right now. And here you can see an historical perspective of that. Ekman spiral. Well, this is along a coast. Say you have winds blowing from the south to north along the North Carolina Outer Banks. Well, what happens is the water starts turning to the right because of the Coriolis effect, and it winds up keep turning to the right with depth more and more. So you wind up pulling up all this cold water from below up above. Sometimes this has dropped the temperature as much as 20 to 30 degrees in just 24 hours along the Outer Banks. It can go from 80s to the 50s. Not pleasant if you're wanting to swim. And here we have El Nino and their impacts, warm phase, cold phase. El Nino, typically in the warm phase, which is where we're headed right now, has an impact more on hurricanes. Believe it or not, it tends to suppress them because we're getting a stronger easterly flow, which develops wind shear. Hurricanes don't like that. We talked a little bit about the North Atlantic oscillation. When it's positive, you have typically cold air masses a little further north in Canada. They tend to be right along the Canadian border with the U.S. more negative. They come down into the United States a little more. We also get stronger nor'easters and stronger lows in the eastern part of the U.S., which might lead to more snowfall. And here you can see positive NAO, strong high, weaker low. Weaker high, weaker, stronger low. So they just rotate back and forth there. And you can see they tend to last. Some winters have a lot of these really obvious ones, others don't. Arctic oscillation, we're just talking about the circulation around the poles. The stronger that circulation is, the more positive that Arctic AO is, the less chance of cold air getting into the United States, to Arctic air. The weaker it becomes, and it will become that during some portions of the winter, that's when the real cold Arctic outbreaks settle in. Pacific decadal oscillation is another long-term oscillation. Kind of works with ENSOs a little bit. There's a warm phase and a cold phase. It has more of an effect on the west coast of the U.S. Madden-Julian oscillation, basically it's a large area of thunderstorms that develop, typically over the tropical Indian Ocean. Think of it as like a jump start to the atmosphere. A whole bunch of air goes up. Well, the atmosphere is all connected. So as it's going up, somewhere else is going down. Because you can't keep all that air aloft. So as this moves along the globe, it can possibly influence where hurricanes develop, or tropical storm, or even extratropical storms, or maybe keep an area drier, depending on which phase you're in of the Madden-Julian oscillation. And they track around the globe in about 30 to 60 days. Really, until about 20 years ago, these weren't real well known. We've gotten a lot better at understanding them. And they're mainly in the winter, and they also tend to enhance what we call pineapple express of a lot of moisture. We talked about atmospheric rivers. Well, they come into the west coast. These can enhance that. And that's really what I wanted to talk about. I hope you got a little bit out of that. And let me know if you have any questions.